Okay, so the compression function basically shuffles the input bits. Now, how does it achieve this thing? That you will see in details in the cryptography course. But for the time being, know that and there are several operations, group operations, group ring field already I have discussed in the previous class, like rotation, substitution, interchange of the bits inside a byte. So byte is usually kept in a register, shift register, and then left shift rotation, right shift rotation, substitution of the content of this register with substitution with some other byte, interchange of the bytes kept in different registers, logical operation between the bits like AND OR etc. at the bit level, and addition and multiplication at the bit level with respect to modulo 2. So how modulo 2 addition and modulo 2 multiplication is done, that also you will learn in cryptography. So a combination of, but all these are symmetric cryptography based operations. No public cryptography operations are executed in the implementation of a hash function. So in short, what is being done, as I have already said, that basically shuffling the bits of the input with the help of some key, or shuffling the bits of the message block with the help of some the previous stage output or initial value. So that way we are shuffling the bits of the input in such a way that the output appears completely random and independent to the bits of the input. That means it satisfies the properties of random oracle. So that is about how to design a secure hash function, and what are the security properties and how it is verified. Now, what are the uses of hash functions in cryptography? Basically, for two different purposes, hash functions are widely used in cryptography. The first one is to achieve message authentication and integrity, and the second one, which already I have introduced to you in the last class, that to implement probabilistic encryption system. So the first one, let us discuss first, message authenticity and integrity. So already I have said that you have already used this thing, used this feature in the internet when you download some software or some other file from the internet from some secure source. Then you also digest some MD digest, MD5 or something, some digest you also download, and then automatically your browser checks the digest matches or not. That means you are not only downloading the message, but also at the server side it computes the hash digest of the message, which is called message modification detection code, MDC. So the MDC is also transmitted to the receiver side. Now the receiver side, the browser, your browser client program, again executes the hash function on the received message and checks whether the generated MDC matches with the received MDC or not, and if they are not same, then it rejects. Otherwise it accepts that the message is intact. Now how can you be sure that this algorithm is working correctly? Because as I have said, that suppose if some bits of the message or maybe some bits of the the MDC is modified during transmission. For example, suppose some bits of the message is modified during transmission. Now this modification can be unintentional due to the error in the channel, or it could be intentional, induced by an attacker to modify the message. Then, as I have said, that the MAC values will not match, and so what the attacker can do, since it has access to the channel, that suppose now you can see it is written that the message is getting transmitted over an insecure channel, open channel. However, the MDC is being communicated using a secure channel. How we can establish two different channels? One is insecure channel where the attacker cannot modify the message, and another is a secure channel that we'll see later, because both of the computers are connected through the same internet connection, say over the internet. Then how can we establish two different channels? One is secure, another is insecure. That I'm coming later. But suppose there exists a secure channel to do this thing, For example, suppose this MDC is being sent using your mobile phone, not using internet, but using mobile phone as an SMS, and this is transmitted over the internet. So if I assume that the SMS communication is secure, but internet connection is insecure, then MDC is getting transmitted over secure channel, and this big file, because the MDC is only few bits, 128 bits or 64 bits, that I can transmit as a string of hexadecimal digits using an SMS, but we cannot transmit a 2 GB file using an SMS. So 2 GB file is transmitted over the internet. But the security we are saying, suppose the attacker is now getting access to this thing only, message only, but it cannot modify the digest value. So can it replace the file intentionally or unintentionally? It cannot, because of the collision resistance of the hash function. Because then, since it cannot modify the digest value is getting transmitted over a secure channel, so it can calculate the digest because it has the message, so it can also calculate what is the digest is not confidential. The attacker also can calculate the digest, but as I have said, given a message, it is very hard, computationally hard, to find another message with the same digest value. This is the second pre-image resistance, and as I have said, the secure hash function has both all of the three properties, so it is second pre-image resistant also. So given the message, it will not be able to find another message whose digest value is also the same. So it cannot do this thing. So in that way, the security is ensured. Now the big question is coming that do we do this thing in this way only, that we transmit the MDC value over mobile phone? No, of course not. Of course, when you download a software from internet, definitely the MD5 is not received over your mobile phone. It is also downloaded from the internet. That means the same internet connection we are using to transmit both the message and the MDC. Then how can we implement this secure channel over the internet? That is secure actually logically, not physically. Physically we are using the same communication path, passing through the same router, same etc. switches, LAN, WAN, everything. However, this communication channel is logically secure. Logically secure meaning secured using cryptography. Secured using cryptography. Now we can secure it using symmetric cryptography, or you can secure it using public cryptography. Okay, so if we use symmetric cryptography to secure this channel, logical channel, then this mechanism will be called message authentication code, or MAC. If we use public cryptography, then this mechanism will be known as digital signature. Okay, now we may be wondering that why then we are not sending the file directly through the logical channel, because as I have said that there is a cost associated with cryptography. Every cryptographic operation has its cost. So if you need to protect the entire file, then you have to execute cryptographic operations in 2 GB or 3 GB file, which will be expensive, which will have a large computation cost. However, if you have to protect only 64 bits of digest or 128 bits of digest, or even 512 bits of digest, then the cost is negligible. So that is the reason that we only protect the digest but not the file. But when you download it, so definitely this mechanism does not ensure confidentiality. We are not, the objective here is not to ensure the confidentiality of the message, but to ensure only, as I have said, we have started the discussion, authenticity and integrity. Authenticity and integrity, not confidentiality. Now integrity, definitely you have understood that if we modify the message, then this side the MDC values will not match. But you are now wondering how are we ensuring the authenticity. That we will see in the next mechanisms when I explain. So this is the symmetric cryptography based mechanism. So what we are doing here, you can see this is the sender side and this is the receiver side. So sender side is doing what? It is concatenating, or it is using the key, symmetric key. So there is a symmetric key between Alice and Bob. The symmetric key is also used along with the message to compute the digest. So in other words, you can say we are computing the hash based on the value of the message as well as the key, the shared secret key, and then we are computing the digest. Then this digest is getting attached with the file, and both of them are transmitted over in a secure channel. At the receiving end, the receiver is again computing the digest from the received file and the shared secret key, which it also holds, and then it is matching the digest values. So this is called MAC. And if you see digital signature, what it is doing here, signing algorithm, these algorithms are called signing algorithm and verification algorithm. So during signature, and this is verification, during signature the sender is taking the message and the private key of the receiver, private key of the sender, Alice private key, and then the receiver Bob is using the public key of the sender to verify the authenticity of the signature. You can observe this is exactly the opposite thing that we do in public key encryption. In a public key encryption, the sender uses the public key of the receiver, because then you need the private key of the receiver to decrypt it, so which is held only by the receiver, so only the receiver can decrypt the message. However, here you see during encryption the sender is using its own private key, not the private key of the receiver, or not the public key of the receiver. It is using the private key of its own, and definitely then the verification will require the opposite thing. That means the verification will be successful if we use the public key of the sender. So that ensures the authenticity part. In symmetric cryptography also you have observed, I think, that how it does ensure the authenticity. Since you are using the same shared secret key on both the sides, so if the digest values match, then Bob is sure not only about the integrity of the message but also about the authenticity of the message, because they are using the same key. If we use a different key, or if it is not Alice, if this entity is somebody else, then he or she will not hold the correct key K, and then also the generated digest values will not match. Similarly, here in the public key mechanism also you can see, since we are verifying using Alice public key, so if the verification is successful, then we are sure that during sending the private key of Alice only was used to generate the signature, which ensures that the signature was generated by Alice only. Now, there are different types of MAC, different varieties of MAC. One is known as nested MAC, one is called hash MAC or HMAC in short, another is CBC MAC or CMAC. This is nested MAC, which is the simplest one. Already I have explained. So you are concatenating. This is a concatenation operation, just adding one after another the key and the message, and then in two stages you are doing it. You are first calculating the digest of the thing, and then again you are concatenating the same key, say or secret key, between Alice and Bob with the intermediate output, and then the final digest is the MAC value. And this one is little bit more not complicated, but we are doing some extra operations. We are using two constant strings which are called input pad and output pad. Two constant strings we are using. So this is the shared secret key, and this is the message. The message has a number of blocks, and we are prepending an extra block with the message, and that block is generated as the output XOR of the shared secret key and the input pad. And then we are calculating the digest, and then this is the intermediate output, and then which we are concatenating with another block, which is again the output of the shared secret key and another constant string which is called output pad. And then the final digest is called the MAC, hash MAC. And this is CBC MAC. As you can see, the cipher blockchaining mode has been used. This is the CBC encryption algorithm. So in different rounds, how many rounds will be required, that depends on how many blocks are there in the message. So this is the shared secret key used, and these are the XOR operations. So you can easily understand this circuit. There is nothing in this circuit. These are the AES or DES block cipher encryption algorithms. And then finally we are generating the digest. So these are the three different types of MAC. Okay, nested MAC, HMAC, and CBC MAC or CMAC. Now digital signature. So I've already explained this thing. A digital signature, exactly, you can assume what we are doing is we are encrypting. We are encrypting the digest value of the message with the private key of the alias, and then we are decrypting, as if you can assume we are decrypting the digest of the message again with a public key. Okay, as if, why did I say? Because actually the digest is not confidential, because you were transmitting the message and the signature simultaneously in the channel, so anybody can calculate the digest. But the point is that when we are encrypting the digest with the private key of the alias, that is not for ensuring the confidentiality of the digest, but only to ensure the authenticity and integrity of the digest. Because the other side, Bob, when he will try to decrypt that encrypted digest with the public key of the alias, then if after the decryption it should match the digest with the digest of the received message. If it matches, and then it ensures both of the things, the integrity of the message and also the authenticity of the message, because since we are using the public key, so it will not match unless otherwise the private key of alias has been used to generate this digest. Let us see an example. This is RSA digital signature mechanism. This is RSA digital. RSA encryption system, already you have studied in the previous class only. I discussed RSA encryption mechanism. So which is doing what? Which was doing, if you remember, I can go back to those slides also if you wish. Okay. So M is the message and M to the power E mod n is the ciphertext. This is encryption, and so E and N are public keys and D is the private key, if you remember this thing. And then receiving the ciphertext C to the power D, we are doing C to the power D mod n is nothing but M. So M to the power E, M is the message and C is the ciphertext, E is the public key, D is the private key. M to the power E is encryption, C to the power D is decryption. So here, as we have said, that we are as if encrypting the digest of the message and we are decrypting the digest of the message, encrypting with the sender's private key. So exactly that thing we are doing. We are computing hash of M, and then that is, say, D is equal to hash of M, and then D to the power small d. Small d is the private key of the sender. D to the power D is nothing but the signature. Then we are transmitting the message and the signature both to the receiver. The receiver is decrypting, in some sense you can say decrypting the S with the public key of Alice, which is E. So S to the power E will give you back D, or you can say this is D dash, and then you can again calculate the digest of the message, which is a D, and then D and D dash should match. Then we'll accept, otherwise we'll reject. Now you can analyze the security of this mechanism also, that if RSA encryption mechanism is secure, then RSA digital signature mechanism is secure. That means the security of RSA digital signature mechanism depends on RSA security of RSA encryption mechanism. Okay, understand this thing carefully, that security of RSA digital signature mechanism depends on the security of RSA encryption mechanism. Why did I say? Because see, this hash function is following the random oracle model. Since it is a secure function we are assuming that it is a secure hash function. So the digests are completely random. Okay, so even if an attacker has thousands or millions of message and signature pairs in its hand, then attacker, I'm saying, so whether it will be able to generate a forged another message and a signature pair signed using the private key of Alice. This is the attacker's objective, to generate a forged message signature pair, which is generated by the private key of Alice, but without having the private key of Alice, because it is attacker, it is not having the access to the private key. Can it generate a valid message and signature pair? Now the point is that since so how do you generate this thing? Now if this is valid, that means the digest of the message and s to the power e will match. Digest of the message and s to the power e must match. Now what is s to the power e? That we have already seen that is something d. Now what is d? Now d is nothing but the digest, that should be equal to the digest of the message, and which is completely random. Okay, so that means, in other words, this was the encryption. This s part was the, as I have already said, that s is the encryption of this digest. Now what is this digest? This is a completely a random string. So if the attacker can encrypt a completely random something to the power d is not encryption, something to the power d is you can say decryption, or forget about encryption decryption confusion. You say that it can do modular exponentiation with the power d, exponent d, with any random string. Then given a ciphertext also, it can raise its power to the power d in modular arithmetic, and ciphertext to the power d is nothing but the message. That means it can decrypt any given message also. That means there is no security of the RSA encryption system. So that means using proof by contradiction approach, we proved in details. We will study also in the cryptography course, but just repeat this video and then listen to it carefully, repetitively, and you will understand what I said. Okay, that by contradiction we proved that if we assume that the attacker is able to generate a forged signature, then definitely the attacker will also be able to decrypt any given ciphertext. That means the RSA encryption system is also not secure. That's why I said that first we have already proved that RSA encryption system is secure. Last day we have not proved that. We said that in cryptography course we'll see that based on integer factorization, hardness of integer factorization problem, it can be proved. Once it is proved that RSA encryption mechanism is secure, we can prove, or we have already discussed the rough sketch of the proof, that the digital signature, RSA digital signature mechanism is also secure if RSA encryption mechanism is secure. Apart from RSA, there are many other digital signature algorithms which you will study in the cryptography course. For example, some well-known digital signature algorithms are Elgamal digital signature, SNOR digital signature standard DSS, and elliptic cryptography based digital signature standard ECDSS. Okay, so this is the end of this slide PPT, and the next discussion will give you a brief introduction to elliptic curve cryptography. Thank you.